Okay, so let's get back to section 2C, where we're looking at integrals, exponential, and logarithmic functions. So we're going to start by defining the value or the definition of the natural log of x in terms of integrals. And this is coming directly from the first part of the fundamental theorem of calculus, which is what justifies our ability to calculate the area under a curve down to the x-axis between the interval AB. Okay, so as we've seen that shaded region you're seeing there is equal to the integral between A and B. So that being the case, the natural log x, or log to base c, let's not forget that ln x is shorthand for natural log of x. And that simply is equal to the log to base e, where e itself is approximately equal to 2.71828. And it's the only log that gets its own spelling, so that tells you how important it is. Log base 10, as we've discussed, is sometimes called the common log, but this is the only one that actually gets its own name. So it's very, very useful in a lot of applications, especially as I know from experience from business and economics and finance, but it can be used in a lot of other areas as well. So basically, what they're telling us here is that if you integrate the function 1 over t, and this little drawing here tells you what it looks like. In fact, we could go back to Symbolab real fast and see how it draws this. I'll just continue to call it t, just to be consistent with the slides. Okay, so yeah, this is exactly what I drew, except that it's showing you here with these dashed lines that these are asymptotes to the function. The entire function is contained within the first and the third quadrants. But in our case, we're only interested in the area from 1 up to x. So in other words, we could ignore the third quadrant and focus our attention on the graph in the first quadrant. And in fact, let me make this even more precise. From 1 to t, whatever t happens to be, I'm sorry, from 1 to x, whatever x happens to be. So this shaded region here is the natural log of x. Okay, now x could be 3, it could be 7, it could be 15, it could be anything. But whatever x is, this shaded region is the natural log of x. Now they've got much better graphs back here. As you can see in the first case, we have 1 over t. Oh, by the way, I forgot to mention this. Let's go back here for a second. You're probably wondering about the t. Because we're trying to integrate and find the log of x. X is the independent variable. We're using x as one of the limits of integration. So we don't want any confusion. So we're not going to write for the function 1 over x dx. So instead we choose some other variable, which in this case is t, so that it's clear that we're integrating over this function 1 over t dt, but the limits of integration are from 1 to x. So that's why we're choosing t rather than x here. And in fact, it could literally be any other letter that we choose. Sometimes when we do this, the t would be called a dummy variable. It means that we're doing the same thing that we normally do with 1 over x dx. It's just that in order to avoid any confusion, we have to use a different letter than the x, because again, x is being used as one of the limits of integration. But anyway, with that being said, you can see what we're doing is we're taking the area between 1 and some arbitrary value x, and whatever that shaded region is, that represents the value of the log. Okay, so in other words, if let's say x is, I don't know, 10, then this shaded region would be the natural log of 10, whatever that is. In fact, We just quickly throw it into the calculator. Just out of curiosity, it doesn't really matter, but it's approximately 1.09, 1.10. Okay. Now, you'll notice in this next section on the right, what they're doing is basically saying, well, what happens if x is less than 1? Well, then we have to handle that a little bit differently, because if you recall the graph of natural log of x, let me draw a little sketch of it for you here. It looks something like this. So basically, this point where the function crosses the horizontal axis is 1 comma 0. So in other words, when x equals exactly 1, the log is equal to 0. And this is true for any base, by the way. If x is above 1, then the log would be positive. If x is below 1, the log would be negative. But it's understood this horizontal axis is actually an asymptote for this function because the log of 0 is undefined. Okay, so the log is undefined, but is defined for any positive number. So let's say that a is between 0 and 1, then the log of a is strictly is negative. Okay. Whoops. It's negative, not less than 1, it's less than 0. If a is exactly equal to 1, then that log is equal to 0. And if a is strictly greater than 1, the natural log is positive. So this discussion we've just been having about the definition of the log really only applies if the a is greater than 1. Okay, so there's on the left, we have x greater than 1, or there, here it's x greater than 1. And so what they're saying is that on the left-hand side, x is less than 1, although it's not going to be allowed to go down below to a 0, rather. So what they're basically saying here is that while the rule looks exactly the same, the area is indeed the shaded region, but it's below the axis. So therefore, it is negative. Okay, it's defined as being negative because it is going to be below the horizontal axis. All right, so we can confirm this by going to Symbolab and asking it for, let's say, the natural log of 0.5. Okay, well, that's not what I was hoping for. I thought it would give us an actual number. That's interesting. I wonder if I have to write solve or something like that. No, it doesn't seem to understand what I want. Well, you know what? I'm finding that Symbolab is fun, but it does have some problems. There might be a way to get around this. It's really annoying. I mean, on any decent calculator, you won't have any problems with this. Okay, well now the computer is not happy. I don't know what's going on, but we don't want to upset it too much. So I didn't get a chance to read that page. Let's see. I thought I had it there, but apparently not. All right. All right, I'll tell you what. Let's just stop messing with it. The computer's clearly not having a good night. Anyway, I'll tell you what. Let me go to my calculator. The natural log of 0.5 is about negative 0.6913. So the log of negative 0.5. No, that's not defined. Sorry. So it's a negative number, but you know, the way we define integrals is that the areas under the horizontal axis are defined as having negative areas. So that's what this is all about. So anything in that region is going to have a negative log. Okay, so as it says here, if a is between 0 and 1, the log will be negative. Log of 1 is 0 exactly, and then the log of anything above that, let's say 1.5, is going to be positive. Let's see what it is. It's approximately 0.405. Okay, so anyway, here's just a specific example. I chose 3. We have the area between 1 and 3 under this curve. And so the integral is from 1 to 3, as you see down here. And that's of 1 over t dt. Now, the definition, the log is here. The integral is ln t. Okay, so you're basically, one is written in terms of the other. So what this means then is that the integral of 1 over t dt is log t evaluated from 1 to 3, log 3, which means log 3 minus log 1, but this one is simply 0. And so you ultimately end up with log 3. All right. Now, what we're going to do here is quickly review some properties of the natural logs. So the derivative of the log of x is simply 1 over x. Now, if you have something, an integral, on the other hand, and by the way, if you notice, this x has to be strictly positive. Okay. The integral, on the other hand, of 1 over u du, whatever u is, and u is just some arbitrary function of x, you're going to end up with log absolute value of u plus c. Okay. So in other words, now this one we just got through looking at. This is log x plus c. But it's more general than that. If you had something like this, then u would be 2x squared. Du dx would be 4x just 4x. And then du would be 4x dx. So what you have here is actually 1 over u du. And that means your answer is going to be the natural log of absolute 2x squared plus c. So U can be literally any function of x. As long as you have that du there, you're all set. All right. So the next slide, we're just going to do some quick reviewing of the properties, the algebraic properties, that is. So, for example, the natural log of 1, and we've already seen, is just 0. The log of a times b is equal to the sum of log a plus log b. The log of a over b is equal to the log of a minus the log of b. And then finally, we have log a to the r power equals r log a. All right. Those it's good review. All right. Now, just a minute ago, we saw that d log x dx is 1 over x dx. 1 over x. Now, what about functions of x? Okay, so this is a very simple case. What we have here is, instead of just x, we have g of x. So that means, again, it can be literally any function of x. And we're going to see in a second that this leads us to the result g prime of x over g of x. Okay, so you can think of this as sort of a special case of the power rule, but it turns out that this is derived directly from the chain rule. Now, what we're going to do is have a quick review of the chain rule and see why this is true. So first things first, you might recall that the chain rule tells us that if you have something like this f of g of x, the derivative, which we can write as a prime, by the way, you could use d notation too. That gives us this result. You could do this too, of course. But I think this is awfully clumsy. I mean, really. So I'll tell you what, let's stick with the notation in the top. How about that? Let me just get this out of here. It's too messy. Now, the important detail here, though, and this is the chain rule. Right? Somewhere along the way in Calc 1, you learned this. But what I wanted to point out here is that the chain rule is applied to what we call a composite function. One function is a function of another. Okay. So f of g of x is what we call a composite function. And so, by the way, you may have seen this written in a slightly different way. Or f g of x, this is a possibility. We also have g of f of x. So I thought I'd throw you a quick example of how this works. Let's say you have something like this. F of x is x plus 4. G of x is x squared minus 7. Now, you know already how to evaluate a function. Let's say that we're trying to figure out f of 3. And then g of 3 would simply be. So when you evaluate a composite function, you're really doing the same thing. If you notice what I've got here, f of g of x means in your function f of x, wherever you have an x, replace it with g of x. Just like up here, you're replacing all your x's with 3's. Here you're replacing all your x's with 3's. But here, I'm replacing all the x's with g of x. In this case, g of x is x squared minus 7. Now, f of x itself is x plus 4. So what I've actually got here is g of x plus 4 And then you substitute g of x into g of x. You've got x squared minus 7 plus 4. X squared minus 3 is your final answer. That's what we mean by f of g of x. All right, so the chain rule is essentially telling us how to differentiate this function, given that it's a composite function. So it gives us a very convenient rule that we can use for any case where we have a composite function like this. So like, here's an example that you might run into quite frequently. Here we go. Y is the log of x. Well, it doesn't seem like it, but this is a composite function. Because we could think of this as f of g of x, where f of x is the log of x and g of x is x. So therefore, y equals f of g of x. Because we have f of x, which is not just the log of x. So it's a very simple composite function, but it still technically qualifies as a composite function. So, but that being the case, we can then use the chain rule to explain where the derivative of log x comes from. Okay. So in other words, this is the chain rule. This is the function. So from what I just showed you, let's let f of x be log of x, and g of x is simply x. So that means that f prime of x is 1 over x, because remember we saw before. And of course, if g of x is x, then obviously it's going to be 1. All right. So g prime of x could be written as dx dx, which is just 1. All right, so here, this is what we're trying to solve for. F prime of g of x is 1 over, now remember, it's 1 over x. F prime, so if f prime of x is 1 over x, then f prime of g of x must be 1 over g of x, because all you're doing is replacing all the x's with g of x's. And that's what I have here. And now g prime of x is just 1, so we don't have to worry about it. And since g of x is just x, the final result is just 1 over x. So this rule is a direct consequence of the chain rule, right? That's where it comes from. So why don't we try another one? This time, it's a little messier because it's not just log of x, it's log of f of x. Now, remember, before we saw that when we have something like that, here it is. Let me just copy this. Just a quick reminder. So again, you may wonder, where did this come from? All right, well, in this case, f of x is again log of x, but now this time g of x is the 4x squared. So therefore, f prime of x is 1 over x. G prime of x is 8x to the first power, or just 8x. That is our product rule. So remember, again, too, based on the chain rule, we're going to have f prime of g of x, g prime of x. So what does that get us? All right, here we go. I've gathered all the information together that we need. So here's the chain rule. We know what f of x and g of x are. We know what their derivatives are. So when we plug everything in, f prime of g of x would be 1 over g of x, which would be 1 over 4x squared. And then, of course, g prime of x is right here. So all we need to do is multiply these together. And so this reduces to 2 over x. And if you notice, based on that rule, remember we were given this rule earlier. Let's confirm that this worked. So g prime of x is 8x. And g of x was 4x squared. In other words, if we just use the rule, I mean, we don't have to derive this through the chain rule every time. We would have just realized that it was 8x over 4x squared, which is simply, again, 2 over x. Okay, so in other words, once you understand the chain rule and how it affects, or how we're using it here, you can just go ahead and plug the results directly into this formula, and you'll have your result. Okay, we don't need to derive it every single time. All right, now this time, we're going to do exactly that. Let's just say we get it, the chain rule is responsible for this. So we have d g of x, sorry, log of g of x dx is g prime over g. So in this case, this is our g. And g prime is therefore just 15x squared from the power rule. And so the final result will be 15x squared over 5x cubed minus 2. And that one, unfortunately, can't be reduced, but that's the final answer. All right. Okay. So one more. It looks like I've got one more example here. We're going to do the exact same thing. We're just going to set it up. We're going to use this rule. The only tricky part here is that the way it's written, log 3x squared, you might remember that the log of x to the n. Well, actually, no, I've written it badly here. We could do one of two things. Why don't we just do this? Just to keep it simple, we could just recognize that this is the same thing as 9x squared. Okay, 3x, the entire quantity squared is just 9x squared, so you might as well just use it. Now, that means that g of x is 9x squared. G prime of x, based on the power rule, is 18x. So therefore, we have 18x over 9x squared. Well, it's just a coincidence that this is the same answer as the last one, but it is 2 over x. All right, so now we can go back and take a quick peek at the integrals. Now, we're going to see a lot of techniques for integrals as we go along, and each one has its own special technique that we can use to evaluate it. And the biggest challenge is ultimately going to be to figure out which one we're looking at. But in many, many cases, use substitution might be the correct way to go. So what you might want to do, if you're not sure, is try a couple of possible values for u and see if they help simplify the results. If not, then you'll have to try something else. But at least give it a shot. Okay. unless you're positive it's something else. I think your best bet is always to start with U substitution as a potential candidate for the technique that you're supposed to use. And by doing that, that be it. But if it's not, at least you'll know right away that that's not the right one. So for this one, what you're going to do, of course, is you always try to let U be the most complicated function. And in that case, du dx would be 2x, or that du equals 2x dx. Now, this is good news because it means that we're almost there. We're only missing a constant in order to have du. So really the biggest issue here is we must have our du, otherwise we can't do this. So what we're going to do is supply it ourselves. We're multiplying by 2 and dividing by a half, so that all of this is now du. This is u. So we've got 1/2 du over u. Why does this matter? Because remember, this is that special case, 1/2 log absolute u plus c, or 1/2 log absolute x squared plus 4 plus c. So yeah, I mean that was the whole purpose of this one. Recognizing that yes, it's U substitution, but specifically where we're going to wind up with a logarithm, because it's the special case where you might recall that actually, let me do this in the next slide. So I don't want the slides to get too cluttered here. Just to quickly remind you, that the integral of x to the n dx is x to the n plus 1 over n plus 1 plus c, as long as n is not equal to 1. If n equals negative 1, sorry, if negative 1, then what we've actually got here is x to the minus 1 dx, or we can rewrite this as 1 over x dx, or dx over x. And this is that special case where we end up with natural log x, absolute x, that is, plus c. All right. Now, let's go look at some algebraic properties of logarithms. And the motivation here is to make sure that whenever possible, we want to simplify our results so that it's easier for us to figure out which integration we need to do. So, like, here's a mess. Luckily for us, we get a couple of 3 powers of 3 here. It may not be obvious right away, but for example, here, log 9 is actually 3 squared. Now, remember, the rule here is that and this is true for any log, it doesn't have to be the natural log. So that means that since we have that here, that means that what we have here is log 3 to the 2nd power. And then here, this is just log 3 to the minus 1. So therefore, we actually do, without maybe even realizing it, have all 3 of them are powers of 3. And so that means, as we've seen, that we have this is our final result. Okay, so I rewrote it this way so that we could see how they combine with each other. Log 3 squared is 2 log 3. Negative log 3 squared is negative 2 log 3. And this third one, because the exponent is negative, is minus log 3. The first two cancel each other out, and we end up with minus log 3. Or if you want to, you can rewrite this as log 3 to the minus 1 or log 1/3. You'll still get the same answer. Okay, now E comes back here. Now remember, E is approximately 2.71828. And just don't forget, log E is just 1. Okay. So in general, there's the log, for example, of base 10 of 10 would be 1 because 10 to the first equals 10. Now, here's a graph that explains this to us. So the area here is integral from 1 to E log x. Oh, sorry, I wrote it wrong. No, it's 1 over x dx. Or actually, in this case, it's 1 over t dt. There it is. Okay. So it's just equal to 1. All right. Now, the exponential function, let's take a look at its properties. And these are really not much different than any other properties you've seen with exponents. E to the p times e to the q is e to the p plus q. This is true for any values anyway, like b to the x times p to the y. As long as the two bases are the same, these rules always hold. It doesn't have to be e. And then this last one, b to the x raised to the y power is b to the xy. Okay, so we know these rules, but we don't want to forget them. So now, sometimes this will help, like I said, simplify the expressions that we're trying to differentiate or integrate, and that will mean it'll be easier to find the correct technique that we're supposed to use. Like this one, well, I mean, this could have been a disaster, but we noticed right away that we have the same base for both of these. And so that's what we're going to do. We're going to derive or take the derivative of e to the 3x plus x squared. Now, we recall that, and we mentioned this already, the derivative of e to the x is simply e to the x. What about functions of x? Now what do we do? Well, now you can see the chain rule is going to get involved. But how? Well, this is what ends up happening. You've got e to the g of x times g prime of x. And that's due to the chain rule. I suppose we could try to derive it. Let's just take a shot at that. Just so you can see why this is happening. So the result is okay, so here's a rule from the chain rule. So let's say that f of x is e to the x. F of g of x would therefore be e to the f of g of x. So therefore, f prime of x, since this, remember, if f of x is e to the x, f prime of x is just e to the x. You're going to have e to the g of x, and then g prime of x is just g prime of x. Well, it's not much of a derivation, is it? It's pretty straightforward because we don't have the functions here, of course. We don't know what g of x is, but it's a very straightforward result. And then once we've seen it derived, we can just use the rule every time. So here, for example, once again, the original function was e to the 3x plus x squared, which we figured out because we used the properties of exponents. So therefore, g of x would be that exponent 3x squared plus x squared. G prime of x is 3 plus 2x. So remember, the rule is that the derivative of e to the g of x is simply e to the g of x, g prime of x. So that's going to give me e to the g of x, g prime of x, or e to the 3x plus x squared times 3 plus 2x. And again, this is all a consequence of the chain rule. Oh, wait, sorry, I copied it wrong. Wait a minute. Oh boy, you know what? I just realized there's a typo on here. This was supposed to be g prime of x. It should have been 3 plus 2x. Okay, I'll fix that. Don't you worry. But yeah, that's 3 plus 2x. Okay. Now, that leads us up to an interesting integral. Now, again, at first glance, this looks like an absolute disaster. Just keep in mind now, in the second case, use a function of x. So why don't we do this? Let's try this. Let's try u being minus x squared. So we almost have that. Not quite. We need the negatives. We have to supply the negative ourselves. So I'll rewrite this as negative e to the negative x squared. So I've actually got negative e to the u du, and I'll end up with negative e to the u plus c. I don't have to change the sign of the c because we don't know what it is. Oh, don't let me lose that negative. Negative e to the minus x squared. plus c. All right. Now, oh my God, we've got some interesting extensions of this coming up. Oh, let me just leave it there for a second so you can double check what you're doing. All right. So now what about, there's some really complicated cases here coming up, but they're all directly related to what we're doing. What if we have something like this? Instead of e to the x, we have a to the x. A is just some real number, which is positive, strictly positive. Well, it turns out that this can be rewritten as e to the x log a. All right. Because remember, b to the log b of x is simply equal to x. In other words, 10 to the log, or no, it isn't, it's b. So. For example, yeah, 10 to the log 10 of 1,000. Oh, no, sorry, I was right the first time. It's x. Yeah, because here's what's going to happen. Log base 10 of 1,000 is 3. Okay. So therefore, let's see. Well, this is getting very messy. Let me just switch to the next page then. So anyway, the reason why that's written like that is so that you can see why the next part is correct. The derivative of a to the x. Now remember, the derivative of e to the x is e to the x. So you might think that a to the x would also be simply a to the x. But it's not, as you can see. Now, in general, you can see directly below why this is happening. The derivative of a raised to any function of x is going to be that function by itself times log a g prime of x. And again, this is the chain rule. Okay. Let's see if we can put this together. So once again, our old friend, the chain rule, comes calling here. So if that's the case, we have a to the g of x prime. So if you allow f of x to be a to the x, and g of x is simply g of x, let's see. Now, F prime is this. As we just saw. So let's see, what are we going to end up with? Okay, so that worked out well. So now the tricky part is let's do this. Based on this identity, I'll just copy this. Actually, I don't think this is coming from the chain rule. This is just a result of the definition of natural logs, because so that would mean that f of x would have to be e to the x. And then g of x would be this x log a. Let's try it that way. I think this will be a little easier, because then f prime of x is e to the x. Now remember, ln a is just a constant. So that means g prime of x is just ln a, or log a. So the derivative then of a to the x will come from the chain rule. In the following way. F prime of x is e to the x, but that means it's e to the g of x. And g prime of x is ln a. But we have this identity. Oh, I wrote the wrong thing. Sorry. This is ln a. But this in turn these are the same thing. Right. And that's exactly what we did here. All right. So again, we don't have to get too bogged down with proving everything in sight. But I think it's instructive to see how the chain rule is what's responsible for these rules that we keep running into. So anyway, the bottom line is what you need to know here is, first of all, this identity was going to come in very handy. And then once we get that in place, we can take the derivative of a to the x and a to the g of x power. And then we can do some integration. We can just reverse these processes. And so those results we just saw imply the following. The integral of a to the x is 1 over log a times a to the x plus c. Now, this is, again, a general case of this one. Just remember, this ends up just being e to the x plus c. The reason why, they are really the same thing is because over here, if you replace this a with an e, you would have 1 over log e, which is just 1, and then e to the x. Okay, so they really are the same rule. This is just the one on the right is a special case of the one on the left. And then here, the derivative of log base a of x is 1 over x log a. And again, recall that d natural log of x is simply 1 over x. So it's the same idea here. And then log e is just 1. And then here, so in other words, these are the same rules that we've already seen, but you have this extra constant. So in other words, when we apply these rules to e to the x, we don't have this constant. That's what separates these from what we saw earlier with e to the x or log x. All right. So in other words, this isn't really new. It's just more general than what we've done up to this point. So just remember, if there was an e there, it would be the same, except now you need that 1 over log a. All right, so let's take a look at one of these. Now, this at first glance appears to be a product rule, but that's not necessarily true, because know that a to the n times a to the m equals a to the n plus m, because they're the same base. We don't have that here, but actually we do. 4 to the x could be written as 2 squared to the x power, which is 2 to the 2x power. So you've actually got d dx, 2 to the 2x times 2 to the x squared. And now I can simply add those exponents. Now, what rule do we know will allow us to do this? Well, this should remind you of something we've already seen. The 2 could be a, and this exponent could be construed as g of x. Okay. So this is the rule we just got through looking at. And in this specific case, a is 2. And g of x is 2x plus x squared. So we get a to the g of x log a. And of course, since g of x is 2x plus x squared, g prime of x must be 2 plus 2x. Now, I don't think there's any reasonable way to consolidate this or simplify it, so you can just leave it the way it is. But that's fine. Now, what about this one? Now, clearly, if this was a natural log, we'd be all set, but it's not. It's log to base 8. So what rule do we know that will help us here. How about this one? Well, actually, it's this one. Let's go grab this rule. And so it just means that A is 8. G of x would, of course, be here. 7x squared plus 4. And therefore, g prime of x would be 14x. So according to this, I'm going to have 14x over 7x squared plus 4 times the natural log of 8. Oh, sorry. Yeah, I'm writing the wrong one. It's natural. It has to be natural log of 8. Ooh, what a mess that was. And then let's try this one. Okay, so now clearly we're going to have a to the g of x here. So what rule? Let's see, which rule is that? There it is. Oh, no, wait a minute. Ah, okay, so we don't actually have this rule. Instead, what we're going to do is we're going to use special properties of logarithms. Yeah, that one. Remember, we saw that earlier. So what we have here is d dx of 4 the x to the 4th power so a of course is 4, b is this exponent, and that means that a to the 4 I'm sorry, yeah, no, 4, what am I doing? 4 to the x to the 4 must be e to the x 4th log 4. Now, how does that help us? Because this can now be, now always remember that this ln4 is just a constant. So now, so we've reduced this to e to the g to the x power, e to the g of x power. That one we've seen before many times. All right, let's go back and grab that one. Yeah, that was a while ago. There it is. Okay, I found it. Okay, so given that this is correct, we've got, oh, yeah, what we're actually doing is differentiating the one on the right. Yeah. So we have E, this is our G of X. Now, G prime of X in this case would be 4 times X cubed times log 4. Or if you want, you can rewrite it as 4 log 4 X cubed. So we're going to end up with E to the X to the 4th log 4 times 4 log 4 X cubed. Oof, what a mess. And there's really nothing you can do with it. There's no obvious way to simplify it. But that's it. That's your answer. Okay. So, all right. Now there's more coming up, but I think we'll stop it right here. Tomorrow, what we'll do is we'll just go back and do a bunch of new examples. I think if there's one area that we need a lot of practice with, this is definitely it. We'll try to make up maybe a master list of all the formulas and keep them all together in one place, and then just practice. After a while, it becomes second nature. So in the beginning, it's very there's a lot to think about, but it's one of those situations where once you've seen it, you start to understand what you're trying to do. We'll just write up a huge list of all the functions we might, or formulas we might need, and then we'll just do a bunch of practice problems. Okay, because this is obviously very involved. So, all right, we'll stop it right here, and we'll see you tomorrow.